Pregherei cortesemente gli amici che ci seguono da casa di confermare in chat se ci sentono. Allora, benvenuti a tutti, ben trovati in questo primo appuntamento del 2024 della Jug Milano e vi inviterei a fare un applauso ai nostri ospiti di questa sera, cioè eDreams ODG o Tech Club di Milano, che oggi compie un anno, giusto? Un applauso. Allora, un applauso per eDreams, quindi colgo al volo l'occasione per ricordarvi un paio di informazioni logistiche. Come sempre, se non avete fatto il check-in, per favore fate il check-in. Non è solo per la vostra sicurezza, ma c'è anche in palio, se volete, una raffle per una eDreams Prime Subscription, che è un grande vantaggio, quindi io vi invito a partecipare all'estrazione. Chi sono Dreams ODG, lo ricordiamo visto che oggi è anche il loro anniversario dell'Hub di Milano. Il loro core business: vendono voli, biglietti per voli, biglietti per alberghi, poche parole per fare le vostre vacanze o viaggi di piacere misto lavoro, vedete voi. Sono in Spagna, Portogallo, Italia dove siamo noi, Argentina. Sono una comunità di più di 600 developers tra back-end, front-end, machine learning, quindi insomma ce n'è di tutti, e sono sempre alla ricerca di talenti. Quindi dietro qua di me trovate dei QR code. Se volete diciamo vedere le posizioni che sono aperte, c'è un QR code per quello. L'altra cosa che vi consiglio sempre è di abbonarvi, ad esempio io l'ho fatto, al loro Tech Calendar, che è un calendario Google molto comodo, così potete vedere insomma se ci sono anche altri eventi oltre al Jug Milano, del tipo non abbandonateci, ma diciamo distribuitevi tra le varie community, e potete anche vedere insomma sempre un po' l'ambiente com'è, che è molto interessante da un punto di vista tecnologico e anche di organizzazione. Ci ho detto, penso di aver tirato tutto. Ok, quindi Jug Milano, incontro numero 151. Stasera abbiamo uno speaker d'eccezione per parlare di un argomento tra l'altro molto interessante e non solo applicabile a Java, quindi vi invito anche agli amici a casa di prestare attenzione. Un saluto anche agli amici a casa. Vi ricordo, giusto brevemente, prima di lasciare a Andrea il talk, iscrivetevi alla mailing list e al canale YouTube di Jug Milano, che diciamo sponsorizziamo tutti gli eventi. Come al solito, in fondo al talk di stasera ci sarà un link per partecipare alla raffle di IntelliJ IDEA. Di nuovo ringraziamo JetBrains per mettere cortesemente a disposizione una raffle ogni volta che facciamo un incontro per i nostri iscritti, e siamo sempre alla ricerca di nuovi speaker. Quindi non fatevi trarre in inganno, mi dicono Jug o solo Java. No, innanzitutto Jug sta per JVM User Group, quindi ricordiamo. Quindi tutte anche le tecnologie gravitano attorno al mondo della JVM, e non solo. Se avete trovato un caso d'uso, un qualche use case che trovate particolarmente interessante a condividere come la community, vi invito a iscrivervi, diciamo a contattare i coordinatori. Ci siamo qua io, c'è Andrea, c'è Daniela in fondo, poi di solito Franz, abbiamo insomma un po' le solite facce che ci vedete ogni volta, se volete. Quindi con questo lasciamo stasera la parola a Andrea per un talk molto interessante. Andrea, a te la parola.
Grazie.
Facciamogli un applauso.
So, welcome everybody. Luca asked me to have this talk in English. I hope it's not a problem for anyone here. And today we're going to talk about probabilistic data structures. So this is an introductory talk. There are some nasty topics, but I think that they are explained in a quite simple way, so I don't think that anybody will have a problem. And 2 words about me. So I'm Andrea Iacono. I'm a software engineer. I've been a software engineer for around 25 years now, so it's a lot of time, but I still love my job, and that's very, very nice. And my personal interests are in algorithms, data structures, AI, data in general. But let's see what we're going to talk about today. So we're going to see some probabilistic data structures for 3 different classes of problems, and which are membership, cardinality, and frequency. And what do we mean with the probabilistic data structure? So usually the normal data structures that we deal with in our day-to-day job are just data structure that contains our data, and then we ask for the data and they gives us back the data. Probabilistic data structures do not work this way, so they actually use less memory, so they do not store the entire data but just some part of it. So what you have in return when you ask some data to a probabilistic data structure is most of the time the correct data, but sometimes maybe it's a wrong data, and we will see how to deal with that. So let's start with the membership class of problems. What are the use cases of the membership? In general, when we get a wrong result, and this is not a problem, but it just implies that we have to compute something more, that is a good use case. So for example, let's make the example of the taken username on when you register on a website. So in this case, let's say that you have we're talking about membership, so we want to know if a specific username is already taken or not. So let's say that we use a probabilistic data structure for this kind of task, and the user put a new username, and the data structure that we're using says that the username is not present, while actually it is, because as we said before, it's a probabilistic data structure, so sometimes we will get the wrong result. What happens then? Then we will try to insert the username on the database, and it's highly likely that the database will complain about the existence of two equal usernames. And so there will be an error, and then with this we understand that the data structure gave us the wrong result, and so we can just return to the user an error message saying that the username is already taken. So this is just to explain how to use those data structures. But where is the good point of using those data structure? Well, actually, as we will see later, they use a really tiny fraction of the memory that we would use otherwise if we put the entire usernames in the data structures. So we're talking about saving memory. This is the main the red line that will go on through the whole presentation. Here I listed some other use cases where membership on a probabilistic data structure comes handy. So for example, Cassandra avoids checking the SS table data files when merging those data on disk. So what happens is that at most it will merge the data already existing. It's not an issue, it's not an error, it's just some more computation. So let's see the 3 data structures, probabilistic data structure that we are going to show today. And of course, on the right there's the XKCD strip, which also is always fine. So let's start with the Bloom filter. This is the oldest of the probabilistic data structures that we are going to see today, and it consists of a bit array of size m and k different hash functions, where a hash function is a function that transforms some data into a number, usually. And the membership condition is that all the bits have to be set. Now we will see this in detail because in this way it's not enough. So let's start with the top row. We want to insert x into our data structure. As I said, we're talking about membership, so we insert data and we want to check if the data has been inserted or not. So we insert x. We apply, as you see up, the Bloom filter is with m equals 16 and k equals 3. This means that the bit set has a size of 16, so we have 16 bit and a 16-bit array, and the number of hash functions is 3. So we apply the first hash function to x, and we get as a result 1. So 1 is the index of the array. Let's say, sorry, I skipped a step. We apply the hash function and we get a number. Then we apply the modulo operator to the number given the size that we wanna modulo the number to, which in this case is 16, so that whatever the outcome of the hash function is, whatever number is, we will just get something between 0 and 15, right? Because we use the modulo 16 as operator. And then we apply the first hash function, we modulo 16, and then we get 1 as a result. So it's index 1, the second element in the array, and at the beginning the bit set was filled with zeros. Now we put a 1 in the second position. Then we apply the second hash function to x, and then we get, as a result, we get 3. And so this is the fourth position in the array, and we put a 1 also there. The same goes for the third hash function, and we put 1 over there. So after we insert the x, we have this, we have the structure that we see in the first row. Then we want to insert y, and then we apply the hash functions to y. We apply the first hash function, and we see that the first hash function, when we apply the modulo operator, then has as a result the number 3. This means that it collides with the value that we saw before. This is not a problem, because actually the bit was already set to 1, and we keep it set to 1. No issue there. Then we apply the other two hash functions to y, and we get other indexes, and we set the bit to 1 in those two other indexes. Then we insert z, and the same, we apply the first hash function, we find another index, and then we set that bit to 1, and then there's a second one, and then there's another collision on the third one. As you can see here, there's another collision because the third hash function of the second element y collides with the result of the third element z. Now, we want to ask our Bloom filter if an element is present or not. So let's check if the element E is present. So E is not part of the set of the elements that we inserted, because as you see above the bit set, we have X, Y, and Z. Those are the 3 elements that we inserted before. E is not present in this list, so we expect the Bloom filter to say to return us a false as a membership condition, right? And we check E, and if we apply the 3 hash functions to E, we get 3 indexes, and we see that the first one is a 1, the second one is a 1, but the third one is a 0. As we saw before, the condition for the membership is that all the bit has to be set to 1. This condition is not met here, so the Bloom filter will say that the element E is not part of the set. Good, it's true. It's a true negative. It really doesn't belong to the set. Let's check the element Y. As you remember, Y was the second element that we inserted in the Bloom filter, and then we are going to check on the indexes that they were already set by the Y, by the insertion of the Y element, and all the bits are set to 1. So in this case, the Bloom filter will say, yes, the element Y is part of the filter. When it comes tricky, let's check the element G. If we apply the 3 hash functions to G, we get indexes that by chance, by the other elements, were already set to 1. And in this case, the Bloom filter thinks, given that all the 3 hash functions map to bit that are set to 1, it thinks that the element has been inserted. And so it will return a true. It will say that, yes, G is part of the set, while actually it's not. In this case, it's a false positive. And we know that. We know that sometimes it happens. So it's not an issue, because, as we said, we will use these kind of data structures when we know that even if we get a wrong result, that doesn't really have any issue with the business logic that we want to implement. But of course, if we just get random values, it doesn't have much sense. So actually, we can define the sizes of the bit set and the number of functions such that we can get a precise error rate. So let's say that n is the number of the expected items. So we expect, I don't know, well, we will see a numeric example later. N is the number of the expected items. And the epsilon is the error rate the false positive rate that we want to the Bloom filter to have. Where epsilon, of course, is a number or a percentage or a ratio. It's just a number between 0 and 1. Then, if given these two n and epsilon, then the bit set size m will be given by that formula, and the number of hash functions will be given by that one. So let's say, let's make an example. If we want to check, if we know that the Bloom filter will have around 1 million items, different items, of course, and we want to have a 1% error rate, so we want to have a false positive only 1 in 100 times that we ask the Bloom filter if an element is part of the set or not. Then m has to be, given the formula, has to be of 9.5 million bits, which is 1.2 megabytes. And the k is 6.6, so it's 7. Of course, we cannot use fractional number of hash functions. And the good thing of this is that whatever the size of the objects we are dealing with, we have a cap size. So we know that it won't take more than 1.2 megabytes of memory. And that's the powerful thing about the probabilistic data structure. In an environment in which you have either very limited memory, I don't know, I'm thinking about embedded systems, or if you have a very big amount of data, in both cases, so the two extremes, you have the way to deal with a fixed amount of memory that allows you to treat the data that you're getting in a safe way. So here we have a graph. If we start from the right part, so if we want to have 80% of error rate, then the number of bit will be 460,000, which divided by 8, it means around 60 kilobytes, which is definitely not, but 80% it's a lot of false error rate. If we want to go down to 0.3, so 30% of error rate, then it goes to 400 kilobytes, and then this is the first one is the example that I showed before. It's 9.5 million bit. So as you can see, the more the curve grows a lot going toward the 0. So the more precision we want in the data structure, the more the memory that we need. It's just a trade-off according to the use case we want to deal with. We are dealing with. We just set the percentage rate that we want to. And a very nice and interesting thing that I found about the Bloom filter is that you know the fruit flies, so the little ones that are used usually in biology for making experiments. Well, those flies have evolved an olfactory neural circuit that basically it's a variant of a Bloom filter. It has two additional features. So when a fruit fly has to understand if it is already smelled something, if it's something new, then it uses the neural circuit in the brain of the flies actually is a Bloom filter. It has two additional filters, but the basic idea is that one. So it's nice that in 1970 we found something that in biology was known by millions of years ago. So here is an implementation. I wouldn't call that production ready, but still it's just to show that in 20 lines of code you can have something basically working. And there's this class hasher, which just returns a very basic hash function. And at line 06, you can see that we created the k hashers that we need for being used for every element. But the very nice thing is that you can see at line 11 and 13 that you have the method contains and the method add. What happens if we actually want to delete an element? Let's see it. So let's see that let's say that the current state is the last one that we saw with x, y, and z. We want to remove x, and then, as you can see, we apply the 3 hash function to x, and the indexes that we found, we just set the bit to 0. But then, at the last row, we check y. Since there was a collision between x and y, now one of the bits that were set to y is set to 0. So when the Bloom filter checks y, it gives back a 0, and then it says that it's not present. Actually, y it's present. So we have a false negative. In this way, if we add delete to Bloom filter, not only we have true positive and true negatives and false positive, we also have false negatives. This means that data structure is completely useless. So deletion is not supported in Bloom filter. What we can do for yes, of course. What we can do for addressing this stuff? What we can do is extend the Bloom filter probabilistic data structure to a counting Bloom filter, which consists now not anymore of a bit array but a count array, and the rest it's basically the same. So let's see how it works. We insert we insert x, we apply the hash functions, and in this case we are not setting bits from 0 to 1, but we are increasing the existing value by 1. So the count array was set to 0 at the beginning. We apply the first hash function, and then we set from 0 to 1. Then we insert y, and as you can see, for example, the first hash function of y collides with the existing, the second existing of x, and so we increase the existing 1 to 2, and we increase from 0 to 1 the others. And the same goes for z. So in this way, when we ask the Bloom filter if an element is present or not, we're not checking anymore if it's all the elements are 1, but we check that all the elements are greater than 0, because now the value can increase. And in this case, E is not present. We didn't insert in the counting Bloom filter, and so it's 1, 1, and 0. The condition of having all the elements greater than 0 is not met, so it's a negative. It will say, no, it's not belonging, and it's true. It's a true negative. We check y. Y was inserted. All the elements have values greater than 0, so it will say that, yes, it belongs to the set, and that's true, so it's a true positive. And then we also have, again, the false positive case. And in this case, G checks for these elements. All of them are greater than 0, even though G wasn't inserted. But still, the Bloom filter thinks it was inserted, so we have a false positive. And why we would use the counting Bloom filter? Because if we need to delete an element, then we just decrease the number of 1 by 1. So we remove y, and then all the bits, all the counts that were set by y when we inserted are removed by 1. So from 2 to 1, from 1 to 0, and from 2 to 1. And in this case, we don't have any false negative anymore. Here is, again, a very small implementation. What we can see here is that we don't check the bit anymore, but we just increase, and which, yes, here there's a bit of difference because on the JVM bytes are signed, so I use the minimum value in order to get the full range of the 8-bit of a byte. But the main difference is that at line 11 we have a delete function, so that wasn't present in the Bloom filter. Still, the counting Bloom filter has some issues and are related to memory. So as I said before, the nice part about these data structure are that they allow to save a lot of memory. In this case, of course, if we are using a byte for counting the elements, it's 8 times a bit, and so it will be 8 times the memory consumption. If we use a short or a int, we will have even greater multiplicators, and of course this is not what we want. And also, it can also overflow. So the moment in which the maximum value, then the update later, it will just go down to the following one. In order to address this, we will see the cuckoo filter, which is based on the cuckoo hash table. So this one is a bit tricky, so we will I will show you how it works. So imagine a hash table, and each item to be inserted in this hash table has two possible locations where to fit into. And these locations are given by two different hash functions. If one or both these functions map to a location which is empty, then I just write the element in that position. Otherwise, if both the locations that I find with the two hash functions are already filled up with an element, then what I do is kick out the existing element. I will put the new element in there, and then I will apply I will try to get the alternate location of the kicked out element and put in that. If the alternate location is already taken, then the element will kick out the one that is there, and I will recursively start again trying to kick out until I find a free spot. So let's see in practice, because with the diagram it's always easier. Let's say that we are inserting x. We have two hash functions. The first hash function is mapped to the array b1. The second hash function is mapped to array b2. So we apply the two hash function to x, and it gives us two indexes, and those are the two locations. And we decide to write x in the first array in b1, and we keep track of the fact that x is an alternate location as that other index on the second array. Then we want to insert y, and y, we apply the two hash functions to y, and those are we get the two different indexes, and then we decide to write y in the first array, and that's fine, and we keep track of the alternate location. Then we want to insert z. Z, as you can see, the first index is already taken because the x is it's there, but the second one is empty. So I will write z there, and I will keep track that the alternate location is the one that is currently occupied by x. And now comes the tricky part. We want to insert w. If we apply the two hash functions to w, they map to two already used buckets in the array. So what w does is randomly select one of the two locations. In this case, it's taken the second one, and then there was z, but it writes itself and kicks out z. So now z it's outside of the array and has to go somewhere else. But the alternate location of z is already occupied by x. And so what x does? Z then kicks out x and writes itself in place of x, right? And then x has to be moved to an alternate location. But luckily, the alternate location in this case is empty. So I can write x there. So this is the way cuckoo hash tables work. Now, cuckoo hashing is quite nice because, of course, lookup is very, very performant. The lookup runtime complexity is constant because we just apply the two hash functions, and the data is either on the first or in the second, no other choice. So it's a constant runtime. The drawback is that the insertion, the insertion can fail because if there's a loop in the kicking out mechanism, of course we arrive in a place in which we cannot do anything else rather than saying, okay, we need to make the bit set, the array that contains those data to make it bigger and refill the whole structure. And given also this drawback, which is a very big drawback, the incredible thing is that the amortized runtime complexity of insertion is still constant. And that's a very nice feature of the data structure because, of course, it's always nice. Now, let's get back to filters, because we were talking about Bloom filters, counting Bloom filters, and this is cuckoo filter. The cuckoo filter is based on the cuckoo hashing. So, in order to save memory, again, we don't store the entire element. So we saw in the example that we have x, y, w, z. So those are the entire elements. We apply the hash function to these elements and we find the location. Actually, to save memory, we do not apply the whole element. We don't save the whole element in the arrays, because otherwise we won't have the memory saving that we are looking for. But we use a fingerprint function that returns at most a specific number of bits, and that is what we save into the data, into those arrays. So how do we do that? We have this fingerprint function that returns a f-bit value. So we shrink the data that we want to insert, and then comes the very clever part of the cuckoo filter. So let's say that we store some data, and then we need, because the element has to be kicked out, we need to get the alternate location. We cannot apply the second hash function to the element because we don't have the element. We just have a fingerprint, the fingerprint result of the element, so it's just f bits. But then the two hash functions are defined in a way that this is not a problem. So the first hash function is a normal hash function of the element, while the second hash function is given by the XOR operator applied to the first hash function and to the hash of the fingerprint. Given the symmetry property of the XOR operator, this means that even if we have one of the two location, we can get back to the other. Even if we don't have the full element we apply the hash function to, we can do that with a fingerprint. That's the really clever part. And then the cuckoo filter is as easy as that. We just check, does the element belong to the filter? And then we just use the check function that we saw. We check the first location, we check the second. If the element is there, good. If it's not, it doesn't. And when is okay, here we have this formula that tells us how many bits per key we have, and this is a bit less as a memory consumption rather than Bloom filter, so the bit-based Bloom filter. So this is a really good achievement. And yeah, this is a very sample code. The thing that I want to highlight in this code is that at line 16 we have a constant max kicks, which is the one that says if we keep kicking out elements and we reach this maximum number, that it means that either there's a loop or there's something that it's not working as expected, given that we chose a proper value of max kicks, and then in this case we will return false. So the insertion is not possible, then we need to reinsert all the elements in a bigger array. And that's it for the membership class of problems. Now, again, with the help of XKCD, we can we start looking at the frequency class of problems. So when do we use the frequency class of problems? Yeah, okay, the frequency is of course the count of the number of times that an item appears in a stream, and we will use the count min sketch data structure. And we will use this data structure when we need the unique number of users of a service or the top k items, network traffic analysis. There's a lot of use cases also in this case for the frequency. So let's see the count min sketch. Again, we use hash functions. Hash functions we will see everywhere today in this talk, because they are functions that allow to get an object with a specific size and transform it into a number with an object with a varying size in memory, because it can be as big as it is, of course, and the hash function transforms it into a number, which is a fixed size. And that's the part. So we reduce the consumption of memory. So again, counting sketch, we have d hash functions. We have an array count of size d by w, which is defined given by these two formulas, where the epsilon is the error rate and delta is the probability of the error rate. So let's make again another example with numbers. So if we want an error of at most 0.1% with 99.1 certainty of that, then we will need w to be 2.7 and d to be 6.9, which is number of functions, so 7. And if you use 32-bit counters, then it will be 76 kilobytes. And again, that's it. The size of this data structure, whatever the number of the streamed element is, won't change. So let's see how it works. So we have a bidimensional matrix, as you can see up above. D equals 4, W equals 16. So the size of the counting arrays is 16, and we have 4 of them. Each one of those rows in the matrix are the ones related to a specific hash functions. So we have 4 hash function, and so 4 rows. Let's insert. Let's say that we want to insert x, because x is passing in our stream. Then we apply the first hash function to x. It gives us 2, so we put it in the third element of the first array. And again, the second gives 13, and so we put in the 14th element of the array, and so on. We insert y, and there's, as you can see, the second hash function gives us the same value as before, so there's a collision, and in this case, we are going to increment the value, so it was 1, and we increment it to 2. And then we insert x again, because it was the first one that we inserted, so in the stream we saw first x, then y, then x is passing again. And we increment the value of x for all the indexes given by the hash functions. So how do I get the count of the item? So let's say that I'm interested in knowing how many times I've seen x passing by. Then the count of x will be given by the mean of the count of the first row. I apply again the hash function of x to x, and I get the position in the array where I wrote the numbers related to x, and I get the value of that. In this case, it's 2, the first row. And then I get the value of the second row at the index that we used to write for x in the second row, and it's 3. And then it's 2 and 2. So the minimum of 2, 3, 2, 2 is, of course, 2. And that is the value given back by the data structure, which in this very, very basic and simple case is correct. If we want to count y, we do the same, and that's it. Here, as we can see, we had just one collision on the second row. But of course, imagine that we have this data structure that is filled with the data of billions of elements passing by. There will be a lot of collisions. Of course, we get the right size given the formulas that we saw before. So in order to have not many collisions, but still collision can happen. And once a collision can happen, if all the indexes that element maps to are colliding with something else, then we can get a higher count, basically, because the collision makes increase the number of the elements that we are counting, and so this is where the data structure is returning some, let's say, wrong data. Again, we use these when we don't need a precise number, but we need something that is acceptable, even if it has a small error. Here there's a very, very basic implementation, but it's 20 lines of code. And let's see the last class of problems for today, which is the cardinality. And so we want to count the number of distinct elements in a collection. And for using that, we use hyperlog-log. So hyperlog-log is actually an enhancement of superlog-log, which in turn was an enhancement of log-log. And I won't see the other two because it's just changing only the heuristic and the way it computes the mean, but I will stick to hyperlog-log. There's a lot of use cases. So for example, if you're if you are a user of BigQuery and you use the approximate distinct function in the database, it will use a hyperlog-log under the hood in order to compute that. So we know that the result is not precise, but it gives you an idea. And the good point about that is that it costs a lot of less money if you're using BigQuery on a very big amount of data, because it uses a lot less computation and data to come up with the result. And then there's other use cases, but we will start looking at the hyperlog-log and the intuition that is behind the data structure. So let's imagine a very big set of numbers. And imagine that those numbers, imagine their binary representation. I think that we can safely assume that around half of them will the binary representation will start with 0, and the other half will start with 1, roughly, of course. But then we can also go further, and we say that probably 1/4 of them will start with 0, 0, and another 1/4 will start with 0, 1. And again, with all the 2 to the 2 possibilities of 2 bits. And again, 1/8 for the 3. I won't go into those because you can see it there. But I think that the intuition is quite clear. So the general rule is that the probability of having a specific set of k bits at the beginning of the binary representation is equal to 2 to the minus k. So 1 over 2 to the k. And hyperlog-log actually leverages this idea. So imagine that we have a big set of items that are hashed to numbers. So again, we have an object in memory. We use a hash function to transform it into number. This number has a binary representation. And let's say that if we are adding to the set a number which begins with 4 zeros, then we can say that it's likely that the set has a size 2 to the 4th, because there are 4 zeros and then 2 to the 4th. Of course, this only works with big sets, so with big cardinality, because if we only take 3 elements, that doesn't work anymore. And also, the hash function must return a uniformly distributed binary representation. Otherwise, there will be some skewed values that will ruin our calculations. So let's see in practice what the hyperlog-log data structure consists of. And it is a hash function, as I said before, because we get an object and we transform that into a number. Remember that we are counting the unique items in a set. And so that item is an object that can be as big as we want, but again, we apply hash function, so whatever the size is at the beginning, it remains of a fixed size, which is the size of an integer, if we are using an integer for the hash function, of course. And then we use, in the data structure, it consists also on an array of integers of size m. Here is the clever part about hyperlog-log. So if we use one hash function, of course, what it can happen is that, for example, let's say we have we inserted I don't know, 1,000 elements, and then just by chance the hash function gives us a 0. If it's 32-bit, the result of the hash function, that means that the hyperlog data structure, we think that the set contains 2 to the 32 elements, which is 4 billion. Actually, it's very, very far from reality. So what does it to avoid these extreme cases, avoid these outliers that ruin the whole calculation? It does two things. The first thing is that it uses multiple hash functions, so that we just don't have one that the value can be skewed. But using multiple hash function takes more time, so there's a performance issue here. And so it does this nice thing that it uses only one hash function, but it pretends it's more than one. So let's say that these hash functions return a 16-bit integer. We can say that we reserve the first b bits, in this example they are 4, to pretend that these four initial bits are actually saying which hash function, which fake hash function we are using, and then the result of the hash function is given by the 12 bits remaining. So let's see some examples so that it's clear. The array m at the beginning is full of 0. And then we hash x, and we find this binary representation of the value of the hashing function. Then we take the first 4 bits, which in decimal are 12. That is the index of the array. And so we put the value, which, as you remember, we say that we are looking for the starting 0 of the binary representation. In this case, the 12 bits there have only one leading 0. So 1 is the number that I'm going to write in the array m, and the position where I'm going to write it is at index 12. And so I will write a 1 there. Then I'm hashing y. Y, the first 4 bits map to the index 5. And so I will write the number of leading zeros of the remaining part into index 5. Okay, I put it wrong. That is the 6th. Okay. But the idea, sorry, it's wrong, but I think that the idea is clear. And if I hash z, for example, the index is the same of before, but this time the number of leading 0 is just 1. And in this case, there was already 4, so I'm not going to decrease that value. I will just keep it because I need the biggest value. How do I get the cardinality of this data structure? So the way I do it is computing a normalized harmonic mean given by this formula of the values of m. So m is an array, it contains a lot of values. I apply this formula, and then I get the harmonic mean and apply a correction factor alpha. Alpha is given, those values are given there. So alpha 16 means that if the size of the hash function, the size of the data type returned by the hash function is 16, I will have to apply 0.673. If the size is 32, I will have to apply 0.697, and so on. So this is the correction factor. And then, given all these formula, we get that the error rate is 1.04 over the square root of m, which is very, very low. So let's see in practice how we count that. If the array m contains all these values, then the cardinality is given by the formula that we saw before, the harmonic mean, the squared cardinality of the array size, and the alpha correction factor, and it will give us 124 and 59. So the nice thing is that, again, so here there are two things that allow us to have to somehow mitigate the possible outline values. One, as I said before, is that we don't have one function, but as you can see, even though we don't have 16 functions, actually we have applied them using the first bit value, so we are avoiding that a single value will skew the entire computation. And the second part is that the harmonic mean, as a mean, actually tends to shrink the outlying values. This means that, look at the example. So in the first array, the third element is 2, and I get 124 and 59 as the expected cardinality. Yeah, and in the second one, the third element is 12, so it's a lot more. 2 to the 12 is 4000, but the cardinality is just a few elements above. So with this harmonic mean, we avoid outline values to ruin the calculation that we did. And in this way, hyperlog guarantees good performance, again, with the caveats that I said at the beginning, sets of big cardinality and uniformly distributed hash function for binary representation. Here is a very, again, not production code, but just to give you an idea that with 20 lines of code, you can have a basic hyperlog code working. And with that, my brief intro to the probabilistic data structure is over. Here you can see the links to the original papers that defined the data structures that we saw today. Also, if you're interested in the code, here is there's the link of the GitHub repository that contains the code that I showed you. And do you have any questions?
Okay, sorry. I will take actually a question.
Okay.
So, as you went through the algorithms, right? So you given us a few example of use cases. Now, what I wonder is that if you had any sort of like a war story or special use case that you remember that in your day-to-day experience sort of like stuck in your head, particularly like for a fun moment or for a crying war story moment.
No, actually, it was I used the Bloom filter a lot of years ago in a project where we had to find if a specific kind of combination of different fuels was used. Yeah, actually, chemical components for a fuel were already used, and since the possible combination were really a lot, and we didn't want to use too much memory for that. We went for a Bloom filter approach, and because we didn't need to delete anything, and it was quite easy to implement, and it worked greatly. I would say that the memory consumptions were very limited. We used something like I think 10% or 5 or 10% error rate we defined, so that the memory used for the bit set was really low, and we needed that because it didn't run on machines that had a lot of memory. And 10% means that 90% of the times the result was correct, so we didn't have to look into the database if that one was already present or not. So yeah, I would say that that was a success story.
Do you have any source? I mean, most of these data structure can be found even on Wikipedia, but there is a specific book or anything that you suggest in order to go through both the ancient or even newer one most used?
So I don't know of any book. You can find a lot of Wikipedia, of course, gives you, let's say, the traditional ones.
Singularly,
You I don't know where to address you exactly. So what you can do is to look at specific libraries that implement, for examples. So there's Google libraries for Bloom filter and Cuckoo filters, if I remember correctly. And those ones also allow to see how to implement it from a performance point of view, of course, because my code was 20 lines, and as I said at the beginning, it was not production ready, and it was not meant to be production ready. But there are a lot of libraries that that have implementation that are nice to look at in order to understand how to do that in a performant way. But no, I don't know any specific resource to suggest you to look into that. Probably what I would do is just to look for specific classes of problems and see if there's and look for probabilistic data structures applied to those, and probably we'll find articles with also the newer ones.
Okay, thanks. Matteo, we have another question. It's fine, or you have to do. Okay.
Thank you, Andrea. Very interesting. I well, it was hard to me follow you under your explanation, but it's very very interesting. Honestly, there was just one thing I would like to ask. It's about the use case, well, or the best practice. No, it's not the correct way to ask. Sorry. For what I understood, this kind of probabilistic data structure were very useful when you are trying to invalidate or trying to understand if something is cached or it's in a database, just to avoid to do the round trip, going to ask the service and coming back. That would be really you will gain a lot of time. It's a kind of I would say gain performance, gain time. Okay. Anyway, but what about the pattern, the best practice? How to use? What's the correct way? How do you use this kind of data structure in a real implementation? And what was wrong for in your first implementation? What do you understood? I don't know if you follow in my talk.
Yeah, I kind of understood what you mean. So if I got it correctly, first of all, you mentioned cache, but with the cache is not a real ideal use case, because actually cache is only in memory and is exactly equivalent of a complete and normal data structure compared to a probabilistic one, and the cache will give you the right result all the times, while the probabilistic data structure will give you an approximate result. So if you already have a cache somewhere, you don't need a probabilistic data structure, because of course it depends. If the cache is distributed, then you need a network access. Then in this case, of course, it's different. I was thinking about an internal cache in the application, but that of course is not the ideal. So it depends. For example, if you work in the embedded environment, probably something that allows you to avoid making extra calls or to keep data in memory is always nice. So if you are dealing with a membership problem or a frequency problem or a cardinality problem, then you know that there are probabilistic data structures that can help you in order to save memory. So this is one thing. But also in application where you don't have memory limitation, but you have a huge amount of data. So that also comes handy, because again, if you get all these items that are passing by in a stream, for example, if you have billions and billions of data passing by, and you don't know exactly the size of them beforehand, so you need to allocate memory and put them in a set, for example, for a membership, and you put them and again and again, then the amount of memory will grow indefinitely. And this is something that when you're dealing with big data, you cannot afford at all. So whenever there's a need of a kept memory sized data structure that can give you wrong results, but still the wrong results are not making business logic errors, but you can just go aside them and then redo something, then is a use case that you can do.
That comes to the question, but we have to build our data structure before working on the data, or we can build the data structure while we are reading the data.
So one of the probabilistic data structure that you saw before, it was for a streaming environment idea. But of course, you mean before writing the application?
Or before processing the data. But while we are processing the, let's use the case of the username, no?
Okay.
I suppose that I create my data structure analyzing all the registered users, and while the user is trying to write his name, I have the probabilistic data structure already prepared to answer my questions. Okay, but while we are processing a stream, that would be useful, but we are processing a stream. We have not already read all the data. They may be.
So you're mentioning about a cold start problem.
Yeah.
Okay.
Right. Sorry.
Okay.
Yeah,
Okay. No. Now I got more your
the point.
question. Yeah. Of course, the cold start is a problem, especially for the streaming environment. What you can do, of course, is saving snapshots. So you have a stream and you save snapshot of the data structure, so that if you have to restart your machine, you can just start from where it began. And again, it's a probabilistic data structure, so you know in advance that sometimes it can give wrong results. So even if the snapshot is not completely up to date, if you lost something in the between, it's not that big deal. You didn't save the time that you would have saved if it have given you the right result, and you have to compute it as if normal. So let's say that you don't get an advantage. The worst case is that you don't get an advantage.
Going on, processing the data, the data structure will learn and being more useful.
Yeah. Of course, it depends. So the stream, if you are in a multi-instance environment, this is more tricky. Of course, you can have instances on each server that takes care of all the data that are coming through the main pipeline. It depends. It really depends on the use case.
Thank you so much.
You're welcome.
Any more questions?
I think everybody's
Vai.
everybody's waiting for pizza.
I think everybody's waiting for pizza, so let's make a round of applause for Andrea.
Grazie.
Thank you, Andrea.
Grazie.
And so thank you from the people from the virtual world, and Edrim Sodigeo, as always, for hosting us. Okay, thank you, bye.